Modern optical satellites can resolve objects as small as 30 centimeters across, revealing everything from individual lane markings on a highway to specific vegetation patterns in a forest. But at their core, these multi-million-dollar sensors function exactly like a digital camera. They are passive, meaning they rely entirely on capturing sunlight as it reflects off the Earth's surface. Because they require that reflected light, these sensors lose their vision the moment they cross the terminator into the night side of the Earth. Even during the day, light has to travel through the atmosphere. Thick cloud cover, wildfire smoke, or seasonal monsoons act like a physical wall, blocking the satellite's view of the ground below. If a major hurricane floods a coastal city or a cargo fleet moves under the cover of a storm, these sensors are effectively blind. The visual data is physically blocked from reaching the spacecraft. This leaves us with significant, unpredictable gaps in our planetary monitoring. We have high-resolution data, but only when the weather and the time of day happen to align. The alternative is active radar. Instead of waiting for the sun to illuminate a target, a radar satellite generates and fires its own energy. Optical light scatters against clouds, but longer microwave radar passes straight through total darkness. However, physics demands a trade-off. To achieve high resolution, antenna size must be proportional to wavelength. Because microwaves are long, a satellite would require a city-sized antenna for a clear picture. Engineering and launching a physical structure of that magnitude is currently an impossibility. Traditional space-based radar forces a choice. You either accept blurry, low-resolution images, or you attempt to build an impossibly massive spacecraft. Engineers bypassed this physical limitation using a method called Synthetic Aperture Radar, or SAR. It uses motion to simulate the performance of a much larger antenna. The process begins with a compact satellite traveling at several kilometers per second along its orbital flight path. As this diagram shows, the physical antenna fires thousands of microwave pulses, continuously recording the echoes. These overlapping echoes form phase history data. By tracking signal changes as the satellite passes, the system captures exact distances for every ground target. While the raw data is abstract, advanced processing algorithms take this massive string of individual echoes and stitch them together. By combining data collected across that flight distance, the system simulates the resolving power of a miles-long antenna. This works in strip map mode for broad sweeps, or spotlight mode, steering the beam to stay locked on a single location for higher detail. The synthetic in SAR means using time, motion, and processing power to overcome the physical limitations of the hardware itself. Because this data is reconstructed from radar echoes, a finished SAR image does not look like a traditional photograph. It appears abstract and requires specialized interpretation to understand. Instead of capturing color, SAR visualizes physical textures. It maps out surface roughness, material density, and even specific moisture levels in the environment. By measuring distance so precisely, SAR can detect ground movement down to the millimeter. It can monitor a bridge subtly warping under structural stress, or track land subsidence long before it is visible to the human eye. Most advanced Earth observation strategies no longer choose between these sensors. They combine the visual clarity of optical cameras with the 24-hour reliability of SAR. By fusing active radar with passive optics, we maintain a continuous, unblinking view of the Earth, regardless of weather or light, effectively closing our planetary blind spots.